start recording? Ah, it's already started. Okay. So welcome to the last Cabri lecture of this academic year. So it's a pleasure to have Jo Dunkley. It's a real honor. So Jo actually started here in Cambridge with her master, and then she went to Oxford for her PhD with Pedro Ferreira. And then she moved to Princeton to work with David Spergel on WMAP, and then back to Cambridge, to Oxford, where she became a professor of astrophysics, and later on again back to Princeton, where she's now professor of physics and astrophysical sciences. And her area of research, as all of you know, is broadly in cosmology. She's a cosmologist in the very broad terms, in the sense that she has been working on many aspects of cosmology from CMB to large-scale structure and so on. She's been combining theoretical models with extensive statistical analysis of CMB data, initially from WMAP, as I mentioned, but then also on Planck, and more recently on using the Atacama Cosmology Telescope. And she's been providing some of the major contribution to the development of what we think is now is the standard model of cosmology, but also tracing the nature, the dark matter and the nature of dark matter and so on. And I think I do not anticipate any of this, because she will be, I'm sure she'll be talking about most of these things in her presentation. I just want to mention that, well, she's also heavily involved in the Simons Observatory and also in the Vera Rubin Observatory, which I think are going to be some of her next major projects. And just to mention that she has received a lot of prizes. I don't list them all here because it would take me a few minutes, and I don't want to, I want to give her time for her presentation. I just want to mention only the last few ones, the New Horizons in Physics Prize, of course, the Breakthrough Prize with the W team with the WMAP team recently. And I will actually want to specifically mention the Royal Society Rosalind Franklin Award, which was given to her not only for her work on the CMB, but also for encouraging more women to study physics. Indeed, Jo is also, as most of you know, very active also in terms of public engagement, and also in encouraging more women in STEM and physics. So I think I will leave Jo to start if you're ready, Jo, and I will move it myself. Thank you.
Wonderful. Thanks so much for the really kind introduction. And it's lovely to see lots of familiar faces as well. I was originally due to give this talk, I think in January, when I had COVID and was isolating with my 3-year-old daughter. And luckily life is looking a little bit up since then. So this is a much better day to be talking to you all. Okay, let me share my screen. Great. So it's a real pleasure to talk about the Atacama Cosmology Telescope and work that we're doing with it to do both cosmology and actually increasingly broader science beyond cosmology too, including a number of people in Cambridge. I'll mention them later. So I'm going to be talking about this telescope. I'll just show you quickly, and then we'll get to the introduction. It's this telescope here. Do you see my cursor, by the way, for when I use it in future? Yes, I see you nodding. A telescope right here high in the Atacama Desert in Chile, on this plateau a little bit away above Alma that you can see over here, and a couple of other CMB experiments here. And actually is the site for the upcoming Simons Observatory, which has actually already started construction on this next door bit of the plateau right here next to it. If I zoom around, this is taken from a drone image. You zoom around and you see it from the other side. It's this telescope here inside this ground screen that's measuring the millimetre sky, and has been doing that actually since 2007. So what's it doing? So this telescope was built to observe the cosmic microwave background. a topic of great expertise there in Cambridge. You have a long history and vast expertise on this topic. It's a telescope built for this, but it's also been doing other things as well. So we've been observing the cosmic microwave background for more than 50 years now. It was first detected actually near where I am now in New Jersey with this telescope pictured here. This radio telescope picking up this signal from the early universe, picking up this light coming from an epoch 400,000 years after the Big Bang, and picking up this radiation that comes from the time at which the universe became neutral. Early on it was ionized. Travel to us and we pick up this light and make this image of the early universe back then. The wavelength of this light today is in the millimeter regime. Down here I'm showing the intensity of the light measured today as a function of wavelength. It's a perfect black body because it comes from this time. It's picking up an image of the time, or light from the time when the universe was in thermal equilibrium, when we had basically no stars, no galaxies, just photons, baryons, and dark matter interacting. And we see it today redshifted down into this wavelength peaking at a millimeter. And so you've no doubt seen in Cambridge, you couldn't avoid seeing this plot, which is this figure, which is of the image of the intensity of the microwave background over the whole sky, most recently pictured over the whole sky from Planck. And here we're looking at this, so it's this image of this, just part of the universe at 400,000 years at redshift of 1100, where the image is showing us fluctuations in the CMB temperature around a mean temperature of 2.7 Kelvin. And so the fluctuations in temperature are very small. They're, tens of parts in a millionth of a degree. And so you see these red and blue, hot and cold and hot spots traced over the sky. What's that showing us? So that's showing us predominantly what the density of the universe looked like back at redshift of 1100. And it's capturing the density of this actually rather featureless universe, this photon baryon plasma with dark matter there as well, where we're seeing just very slight variations in density across the sky. And these will be the seeds of the cosmic structure that then grow from these later on to form the earliest galaxies. So we get the snapshot over the sky. Planck has also measured the polarization of this light. So more or less, not quite, the intensity of the light captures what the density of the universe looked like at redshift 1100. The polarization of it captures the velocity of what the structures were doing back at redshift of 1100 at that same time. And essentially what happens is the CMB photons that travel to us from that time become polarized if they scatter off electrons that were falling into gravitational wells. So overdense regions have things falling into them, and then the photons that scatter out to us are polarized due to this velocity at recombination. So Planck measured the polarization over the sky too, and have been increasingly building up statistics of things that we can get from this image. So the primary statistic that you take from that image is the angular power spectrum. That's, with significant leadership there in Cambridge from George, from Stephen Grattan, and others in Cambridge, measuring this angular power spectrum, which decomposes that map, takes the image of the sky and looks for the amount of structure or the variance or the amount of bumpiness as a function of angular scale, ranging from all sky down to sub-degree scale here. And this power spectrum has been, and still is, really the most used statistic from these data, because every universe looks unique. We can predict it very precisely theoretically, and we modify the ingredients and the initial conditions of the universe until we find the theoretical curve that fits the data. And so the Planck data are best fit. The red data here, it's been updated, but it's still similar, fit by this LCDM cosmological model. It's got just 3 ingredients, baryons, dark matter, a cosmological constant. It's got two initial conditions that describe how the initial features are described in the very earliest moments of the universe. And that's basically it. It's flat, geometrically flat. It's described by general relativity. That's the model. So that's predominantly come from this power spectrum, in addition to actually increasingly polarization, which I'll get to. But the thing that's sort of new that Planck has begun, and now we're continuing with this with ground-based data, is the use of the millimeter sky for not just that primary, that image of the CMB at redshift of 1100, but for other things too. Because when the CMB travels to us, it picks up secondary effects from the large-scale structure in the universe, as well as the telescope simply being sensitive to any millimeter light that's coming at us from the universe, which includes our galaxy and includes extragalactic sources that are emitting in the millimeter. But these secondary effects, these traces of large-scale structure, I'll describe three here that I'm going to come back to, which is the gravitational lensing of the microwave background. It gets bent around cosmic structures. So the large-scale structures that it travels past distort it ever so slightly by a couple of arc minutes or so, and makes us sensitive to the integrated mass in the universe. And then it also is sensitive to pressure. So hot electrons in galaxy clusters, the CMB scatters through them and picks up this thermal Sunyaev-Zeldovich effect, which just shifts the black body CMB spectrum a little bit and allows you to find clusters and measure the pressure in those clusters. And then finally, the kinetic Sunyaev-Zeldovich effect comes from the Doppler effect from the CMB photons scattering off moving electrons and just imposing a tiny little Doppler effect from the motion of large-scale structure where there are electrons to scatter off. So we're sensitive to all these things. And lots of these, one is more sensitive to the higher the resolution you look at this image in. So some of these things, plenty of these things have been observed by Planck already. This is an image up here of the top image is the gravitational lensing map inferred by Planck, which Anthony Challinor there and many others in Cambridge have played a big role in, where what you're seeing here is the inferred integrated mass from here back to the CMB. It's typically dominated by structures at redshift 1, 2, and 3-ish range. But this map says where it's darker, there's more matter doing the deflecting of the CMB, and where it's lighter, there's less. So just by looking at this, you're able to see the integrated mass throughout the universe. And down here is the nice image of non-CMB, of dust emission. If you pick up the light at just under 1 millimeter, then the colors here show the emission from warm dust grains heated up by starlight and then emitting thermally, that you then see tracing out the galaxy. And the lines come from the magnetic field that you get to measure because the dust grains that emit line themselves up perpendicular to any magnetic field and emit along their long grain axis, such that the polarization that you see in the millimeter or submillimeter tells you directly the magnetic field of the galaxy. So these are some of the things that have been, Planck has been making inroads on these things. But what I want to talk about is how we can go further, and we are already going further than this at higher resolution by adding new ground-based data. And so this is, I'll show you another picture of ACT, I showed you one at the beginning. So the Atacama Cosmology Telescope is then pictured in a little more detail here. It's this telescope that's up at this 5,000 meters elevation, one of the two best sites currently on Earth for looking at the CMB. If you can't be in space, you want to be either here in Chile or down at the South Pole, because the water vapor above you is very low. That's what you want if you want to measure light of this wavelength. And so what you're seeing here is a 6-meter aluminium primary dish. and it's got a secondary aluminium dish as well, and then focuses the light into a receiver that holds thousands of bolometer detectors that can measure very sensitively the microwave light or millimeter light that we're after. The nice thing about being on the ground is that, yes, you've got the atmosphere above you, but you can actually go and change things in your telescope. So we've put in like 3 successive cameras or receivers into inside the telescope to improve the sensitivity over the years. So we started in 2007. It's now 2021. We're on receiver number 3, and we're getting towards the end of the ACT observation time. And so we are a collaboration of about 100 or so people, including a growing group in Cambridge led by Blake Sherwin. So that it's now really active, the Cambridge group, and we're getting lots of great assistance on projects that also use Planck from Anthony Challenor, from Stephen Grattan, and from a lot of the students and postdocs. So that's really exciting. And it's got another year or so to run. We're towards the end of our observations. So this is a little schematic. I'm going to show in a minute there's some detailed maps that are coming out of that, but just to kind of orient yourself. I'm just showing a comparison of what we have from Planck and what we have from sort of the combination of Planck and ACT together. On the left side, you see Planck's got the whole CMB sky, and this is the Galactic emission in red from the Milky Way pictured here. And here over this side shows you the kind of sky coverage of ACT. So we're now seeing about half the sky from the ground, which is quite a big change. We never used to do that with ground-based CMB experiments. We did little bits of the sky. And then we realized that actually we could do the best science, or the science that we were excited about, perhaps most, if we went really wide, which you can do from Chile. A comparison down here shows a little 4x8 degree patch of temperature fluctuations and polarization fluctuations, where with the ACT data, you can add to Planck and zoom in at higher resolution and finer details in temperature and in polarization, and I'll show you this in a bit more in another slide. So what I want to do is I'm going to screen share a different thing in a sec. I'm going to show you this web atlas of our data that's on the Lambda public website created by our collaborator Sigurd Ness. So what I'm going to do is I'm going to just go into that instead. So all of our ACT data is on the NASA Lambda website. And this little web atlas has a combination of Planck ACT and Planck plus ACT maps of the sky. And you can zoom in and out, and I'll show you it a bit here. So here I'm showing you like a 1 degree grid of the sky, where you can see what we're seeing in the CMB and other emission on the sky here. This is a combination of ACT and Planck data. What you see is CMB mostly at high resolution, these blobs, the red and blue blobs, they're CMB. These dots are not the CMB, those are galaxies. Those are mostly blazars that we're seeing in the radio. If I just toggle back to the Planck data, actually I'll be a bit kinder because the Planck data is even better at 150 gigahertz. This is 150 gigahertz, 2 millimeter wavelength, where the sky seen by Planck is shown here. And then, sorry, then I'll go back. And then with ACT added to it, we see it comes up right in high resolution, and you see the galaxies pop out, these point sources. And if I go over to a little bit further over, what you should see in the ACT resolution sky is you see these blue spots. Those are galaxy clusters. Blue is cold in this color scale. Red is hotter. And a cluster shows up as a little cold spot at 150 gigahertz because of the Sunyaev-Zadovich effect shifting the black body spectrum. So we can find galaxy clusters in our maps just by looking for little compact cold spots of a given sort of radial profile and a given frequency dependence. And again, Planck sees a lot of clusters over the sky, but at high resolution, you can't see this kind of thing. It pops out, right? You can just see it popping out with this high resolution. If I go out a bit further, I'll just show you again this idea that we are now able to make maps of the sky that optimally combine the sort of best of Planck with the best of these new ground-based data. So this is what ACT sort of is able to see by itself. You'll notice the large scales on this map have gone, right? If I go back, this is the combo of ACT and Planck together. If I go just to ACT, you should see the small scales there, but the large scales have gone. That's because from the ground, we can't really see the large scales because the atmosphere is confusing to us with the large fluctuations in the CMB. We just can't do that. We can't figure those out from the ground. But no matter, because Planck did it already, so that's fine. You've got the large scales from Planck. And if I zoom out even further, you can see that the extent of this new map, this is this combo of ACT and Planck together. It goes all the way around the sky. These coordinate systems are in our right ascension and declination. So you see it covers from declination like -60 to 20, and then all the way around in right ascension, with just this missing part over here and the bits of the sky that we can't see from Chile. And then I'll show you too that if I go back in, the polarization is really coming into its own. So if I flip now to the polarized signal of the CMB, I'll go here. These blobby red and blue spots are now actually becoming a good signal to noise measurement over quite a wide patch of the sky of the polarization of the CMB. And again, if I go sort of back to just Planck by itself has got excellent statistics over the sky, but on a given patch, it's noisier. This is noisier, this image, than if you then zoom in with ACT, for example. And so ACT is now getting to see like quite high signal to noise polarization, these blobs, over a huge amount of the sky. You see this is the galaxy here emitting along the galactic plane. So let me go back to, I encourage those of you who like to go and play with that Web Atlas. Go back to my slides. So one of the things, we haven't yet done all of our cosmological analysis on the latest maps we have. As you might imagine, doing precision cosmology, and as you I'm sure know from experiences with George and others, it takes a while and you want to get it really right. One of the things we did do an analysis with a subset of our data that we took up to 2016, and computed our own power spectra, our sort of classic signature of the CMB from just ACT, now not combining with Planck, just ACT by itself, because we really wanted to see whether we were getting consistent results with Planck, partly to sort of maybe allay worries in the community that, you know, there's the Hubble tension that says there's a difference between what the CMB is inferring for the Hubble constant, assuming lambda CDM, versus what some of the supernova direct measurements are getting. And is this a worry? Could it be that that there are, you know, systematic errors in Planck? Of course not, we say, but it's always good to go and measure it again. So here we're measuring sort of independently the shape of this typical signature of the CMB. And this is the angular power spectrum as a function of multipole of angular scale, down from large scales through to small scales. And we see the fluctuations in intensity, these acoustic peaks that are the characteristic signature of our lambda CDM model. And we see these acoustic peaks also in the E modes, which is basically the polarization signal. We don't need to worry about the different types of it, but it's the dominant polarization signal. And it really is seen in higher signal to noise. Like, one thing to say is that this intensity peak fluctuation is at a characteristic scale of like 1 degree. There are also peaks at smaller scales, but this 1 degree is like where the biggest variance should be. In polarization, the peak variance is actually at smaller scales. It comes from the polarization tracing the velocity versus the temperature tracing the density more. And you can see that in this little image, which is a snapshot from ACT of just a 25 by 10 degree bit of the sky in intensity and polarization, now high signal to noise polarization. And what your eyes should see is that the characteristic scale that your eyes pick out in the intensity is a larger scale. They're larger blobs than in the polarization where they are smaller blobs. And so the characteristic scale of those blobs in polarization matches up to the fact that we see these acoustic peaks with these characteristic peak variance in polarization, and that it's smaller than in temperature. And so this is a kind of this is a flavor of the beginning, that soon we're going to have this kind of high signal to noise polarized CMB map that's going to be as good in terms of signal to noise as Planck's was in intensity. And just quickly in passing, you've heard a lot about this, I'm sure, from George and others, but we did indeed find with this subset of data that the Hubble constant we estimated from ACT without any Planck data, but with a bit of large scale information from WMAP, was also 67, agreeing very, very well with the Planck result, and also with other large scale structure measurements of baryon acoustic oscillations. Maybe of no surprise to some, but felt somewhat reassuring that we were seeing something very consistent from the early universe measurements. But what I'm excited about that we're doing at the moment, we haven't got results for yet to show, is the fact that until sort of last year, the data that we had from the ground was only sort of deeper than Planck's over part of the sky. But the data we have now in hand is deeper than Planck over half the sky, which means that in this next phase of analysis, we should be able to place tighter limits on cosmological parameters in combination with Planck than Planck could do alone. Let me just show you this plot to show you where we're going. This is our way of sort of characterizing how good our images of the CMB sky are. It characterizes like the depth, like how well you can measure the image in terms of like microkelvin arc minutes, which says in an arc minute pixel of the sky, what's your noise in that measurement? And it's showing this as a function of cumulative area over the sky, like how much sky do you have that good a depth over? Planck, on average, combined over the sky, has a noise level or a depth that's up here at about 25 microkelvin arc minute over actually all the sky, because it's a satellite. The cosmology that we published already had this dashed curve, which says that over 4,000 or 5,000 square degrees of the sky, the noise level or the depth is better or lower than Planck's, but over the rest of the sky, it's higher, right? It's not as good as Planck. And so we were able to do something with that, but we weren't able to be sort of, really take the next step. But the maps I just showed you in that web atlas were these DR5 maps from ACT, where the noise levels are now lower than Planck's over 15,000 square degrees of the sky, coming down in some places to 5 times lower noise than Planck's. And the stuff that we're analyzing at the moment that we hope to do our next cosmology analysis on is this data, this yellow curve, where it's deeper than Planck over about 18,000 square degrees and reaching down to sort of 2 then and 3 times lower noise. And it's at about 5 times the resolution. We'll always need the Planck data at large scales, because again, we can't see through the atmosphere. But with that, we're really going for like tightening cosmological parameters on, for example, the existence of extra-relativistic species, on shrinking the Hubble constant error even smaller, and testing the models that might increase the Hubble constant, things like early dark energy or interacting neutrinos, or probing the primordial spectrum as well. Those things are really then taking this step. That's what I'm very excited about this. This is what we're working hard on at the moment. And luckily we're having some assistance also from Stephen Grattan and student Eric Rosenberg, who are sort of helping us look at the comparisons between Planck and ACT as well. So that's great working with people in Cambridge on that. So that's the redshift of 1100 stuff. But I want to talk. So what else? There's lots of other stuff too. Coming in a little bit in redshift, down to the sort of redshift, I said 1 to 3 or so, is the gravitational lensing. And this is work being led by Blake Sherwin and his team there in Cambridge, and others in ACT as well, and with lots of expertise from Anthony Challinor as well. And this is now, with this higher fidelity image of the CMB, they and others can now reconstruct an even higher fidelity map of the gravitational lensing, the integrated mass from here to redshift of 1100. And this image is showing overlaid on a background. These colors are showing really the hit count, the weights that we're seeing the sky with ACT. And in front of it is this new preliminary image from the lensing group in ACT. Which shows these fluctuations are now becoming, again, high signal to noise measurements of the actual measurements of the integrated mass along the line of sight out to the CMB over quite very large regions of the sky. Obviously, Planck already saw the whole sky, but in the past, we've then only been able to zoom in to smaller regions with ACT. And down here, this is just this shows the sort of response, the sensitivity of the lensing as a function of redshift. The CMB is picking up signals, lensing signals, large-scale structured distortions, all the way from redshift 1100, peaking at redshift 2 or so, down to 0. And there's very interesting overlap with large-scale structure. This is the Rubin version of where it's able to pick up the large-scale structure distortions from lensing, which peaks at slightly lower redshift, but does have quite a good overlap too. So there's all sorts of exciting prospects for cross-correlations of the lensing signal with large-scale structure. And Omar there at Cambridge already has this preliminary plot showing like an 80 sigma cross-correlation between this new map of the lensing with a large-scale structure map from the Unwise survey. And so being able to just go to measure this integrated mass even better will let us put new constraints on neutrino mass, on the amplitude of structure formation, anything that affects the amount of dark matter, the amount of structure integrated along through cosmic history. This will give us a better measurement of that. So that's work underway, and do talk to Blake about this area. Then we have clusters. So coming in a little bit, well, similar redshift actually, our cluster sample goes out to about redshift, just under redshift 2. So again, by looking, I showed you before, you find clusters in the map by looking for little cold spots. And in practice, you actually filter the map to look for things of the right scale, and you also look for things of the right frequency dependence. And that's enabled us to get a new catalogue of galaxy clusters from these new maps from ACT that have more than 4,000 confirmed clusters with redshifts. And this is the largest Synyav-Zadovich catalogue of clusters to date. We were looking back and realized that our very first ACT data release, we had 23 clusters, and now it's more than 4,000. So going wide does get you quite a long way. Oh, I'm so sorry. I went back to my slides and I wasn't playing them. I'm sorry, but I hope you could see them anyway. And this is a little snapshot from Matt Hilton of co-moving megaparsecs from us and where the clusters are. And you also see them down here as a function of right ascension declination. All our clusters are shown in these crosses, with the grey boundary region showing where we see with ACT, and behind it you should be able to hopefully see the Dark Energy Survey unique outline, which shows how much overlap we have with the Dark Energy Survey. as well as actually KIDS and hypersupremecam. So this amazing overlap with optical surveys means that you can find the clusters through the SZ effect, which is really cool because it's redshift independent. So you can actually find things out to high redshift if they're there. And then you can get their redshifts with the optical surveys. And you can also use the optical surveys to get an estimate, a better estimate of the mass of the clusters, because you can use the lensing from the optical surveys to weigh the clusters very well. And so I'll just, actually no, I won't, for reasons of time. I had a little graphic of where the clusters are compared to Planck, but I think I'll save that for now. And so just from taking the estimates, we're still in the middle of trying to do cosmology with our sample of clusters. So I'm showing you here the masses of these clusters, these 4,000 clusters or so, in terms of 10 to the 14 solar masses. So this is, so they go down to about 2 times 10 to the 14 solar masses, is this sample in blue of the ACT clusters as a function of redshift, with the highest confirmed one at 1.9, but there may be more, but we just haven't got redshifts for them yet. So what do we want to do with that sample? There's all sorts of cluster astrophysics that's interesting, but if we can only track very precisely the number of clusters as a function of mass and redshift, that gives us another handle on the growth of structure in the universe. And it can tell us about the neutrino mass sum and about dark energy evolution, because that statistic is going to be rather sensitive to those quantities. The challenge with doing cluster astrophysics is that you can find the clusters in the CMB map, but you get a measurement of this, not of the mass, but of the Compton Y parameter, which relates to pressure in the cluster. And so if you really want to do the cosmology, you have to be able to relate that well to the masses. But that's what we're able to do, or in the process of doing, by using the overlap with optical lensing surveys to get the masses from cosmic shear. And actually also you can combine the CMB lensing as well with that to get the masses, which is people in Cambridge are doing too. So that's still underway. I think that's having this huge cluster sample will help, I hope, help us now take this step of actually trying to do precision cosmology from these ESSA clusters, taking that step beyond where we have got to already. So coming in a little bit in redshift, that my steps actually are coming in towards us from the furthest to the nearest. So now we're going to think about the finding, how we can find the baryons using the kinematic Sunyaev-Sadovich effect, which we're going to be looking at about redshift, things happening about redshift to half. Here I mentioned earlier, this is this effect where the large scale structure in the universe, the velocities of the electrons in the universe imprint this little Doppler shift in the CMB. And this shift, this change in temperature of the CMB due to the KSZ, the relative change compared to the underlying one, is this integral, line of sight integral, that depends on the velocity. Sorry, I've got my zoom box in the wrong place. On this term Q, which is the velocity and captures the overdensity. It cares about the number of electrons. How many electrons are there? So it cares about the overdensity in baryons and the overdensity in ionization fraction of those baryons. So you need electrons and you need them to be moving, okay? So this is a very small effect. Down here, I'm showing you a little simulation of the relative size of these effects. This is like the primary CMB that we look at normally, and a little snapshot of the sky, where compared to the expected signal from the KSZ signal in temperature units, and you can see this is very much smaller, smaller color scale, right? 20 times smaller. And you just see this little red and blue spots, which are the Doppler shifts of things either moving towards or away from us, electrons in the large scale structure moving towards or away from us. So it's incredibly hard to try and pick out this signal from just the map of the CMB that you get. So instead, you use large scale structure catalogs to find them. And so We find them by stacking the ACT maps on galaxy groups that have already been found by the BOSS spectroscopic galaxy survey. So you see, I know where the galaxy groups are. I'm gonna like find them all, gather up all the little like thumbnails of the CMB map around the galaxy groups and add them all up together. And I'm gonna see if I can find the signal. And it turns out we can. So this is a couple of papers led by Manu Shan and Stefania Amodeo at the end of last year, which, let me walk you through what this image shows. This is this stacked up signal of the net KSZ effect, weighted by inferred velocity of the galaxy group, so that everything turns out to have the same sign, so we can add them up rather than cancel them. So this is the total signal in the KSZ as a function of arc minutes from the middle of the galaxy group. And you can also turn that into co-moving radius instead in megaparsecs over h. And so what are we seeing? We're seeing that and it's cumulative. So it says, how is the cumulative signal increasing as I go out in radius from the middle of the galaxy group? And we see two different measurements, two different wavelengths, just to check we're seeing the same thing. And so this paper shows that we detect at about 6 to 8 sigma aggregate, this measurement of this KSZ signal and how it increases as a function of distance from the middle. And why is this interesting? Well, it's interesting because this signal is measuring the cumulative baryons as a function of radius from the middle of the galaxy group. And it's quite hard to find baryons. So we're often asking the question, where are the baryons and how are they distributed as a function of distance around, cores of large scale structure? And what this shows is that the radius of the baryons being distributed is much broader than, for example, an NFW profile that you'd expect for dark matter. These little curves show cumulatively how this signal would be expected to quickly increase as a function of radius and then plateau if the baryons were just tracing the dark matter profile around these galaxy groups. The fact that actually it takes a lot longer, they go out much broader, is telling us something about where the baryons are living. And so that also combined with measuring the thermal effect for the same galaxy groups lets one really test models of feedback prescriptions in hydro simulations. So for example, over here, the Stefania Amadeus paper compared the data we get from ACT with the prediction that you would get from some existing hydro sims, which kind of underpredict what the baryons should be doing at large radius from the middle of from the galaxy group. So hopefully this will help. You want to basically make sure the hydro sims can match up with the data, and the data are going to get much better with as you go even for the next few years. So I think that's quite exciting. Let me just show you a couple of things in the last few minutes. So those are all things that we get to see from the CMB. So I want to show you just a few things that we can get that aren't CMB at all, that they're just their millimeter emission. One of them is point sources, galaxies, distant galaxies. These little images compare what I showed you in snapshot before with the maps, comparing 9 square degrees of sky, comparing Planck with ACT, where you see these sources just pop up all over the place. This is at 9 square degrees out of 18,000. We're seeing about at least 1 source per square degree. And indeed, we have now, if I look at that whole map I showed you earlier, there are about 20,000 of these sources now across the map. Now, what are they? They are blazars, and they are dusty star-forming galaxies. Most of the ones you can see in this image are blazars. And the exciting thing is there's so many of them, and we have years of observations, and we're just realizing the excitement of being able to actually map their fluxes in shorter cadence than, for example, just every year or every few years. We're realizing that you can map them every daily to monthly to start revealing like variability of thousands of blazars in these wavelengths that haven't really been mapped over such large areas before. Little snapshot in the corner shows you just over a few months, a number of years ago, how a couple of these blazars were changing their flux in Janskis over just on month timescales. So this realization that we have this sort of rich data inside the data that we haven't even fully analyzed is we're getting quite excited about, including for looking forward to new data from the next observatory. If we come nearer into the Milky Way, this shows you how dust emission in the Milky Way comes into, already beautifully measured by Planck over the whole sky, comes into higher resolution, higher detail when you add the Planck data. You see these like dusty filaments and features. This is from Planck, and this is Planck and ACT together. You see this information just pop out, this filamentary details. And actually just this morning, our colleague Yelan Guan put out a paper on the archive of a dedicated mapping of the data in the Galactic Center itself. This shows the Galactic Center 2 degrees by 6 degrees around that Sag in the middle, in top intensity and bottom in polarization. And we'd seen this at these wavelengths, in Planck data, but this is now 5 times the resolution at 90 to 100 to 220 gigahertz. The color scale is red for 90 gigahertz, where it's more synchrotron dominated, and blue for 220 gigahertz, where it's more dust molecular cloud dominated. And so you see in intensity and in polarization, there's this very strong polarized, this is the well-known radio arc in the Galactic Center and Sag here, and lots of good details, good stuff with molecular clouds that people are busy looking into. You can see too, this is a zoom in from, again, an ACT plus Planck combination, where we're now looking at the magnetic field structure inside at the Galactic Center. And as has been seen in other observations, you see this strong flip of the magnetic field lines to this like perpendicular direction around the radio arc in the Galactic Center. That's there more in the lower frequencies where it's more radio emission, and then it goes away at the higher frequencies where it's more coming from dust emission. So that's just a quick. There's lots more in that. Lots of beautiful images in that paper. And I know I need to stop. I just want to mention 2 things, and I will stop. 2 things that we've done, really led by our colleague Sigurd Ness. We didn't expect to, but we found kind of by mistake transients in our data. And this is opening a whole new window of things that we think are exciting about these kind of observations. We found 3 flaring stars in our ACT data. These little thumbnails show, as time passes, just 3-day images, 3-day maps of a bit of sky in multiple detector arrays in our experiment. And you see only CMB, and in the last one you see pop up this transient. And it's super bright. And there's another one down here, that was what we call event 1. Event 3 shot up to 300 millijanskis in a day, and then fell down over 3 days. And we didn't really know what these were to begin with, and then we realized that Sigurd, with his excellent work, found that they were all associated with stars, and that this is known. We just didn't really know it inside our collaboration, that it's probably coming from magnetic reconnection of coronal loops on the surface of young stars, particularly in binaries. And these were actually found by chance, and so now we're really digging back into our data to see what more is there, because the possibilities for like transient both in the galaxy and extragalactic, we think is really exciting. Very last, and I'm sorry I did it a bit too short, also led by Sigurd Ness, you can use ACT to look for planet 9. It turns out that it's pretty good for looking. So it turns out that it's just as sensitive as pan-stars, actually, pretty much. This shows the expected flux as a function of wavelength for different kind of most optimistic and most pessimistic models for Planet 9. And the sort of possible detection significance from ACT is in the dark red. And so the most optimistic, the brightest possibility of Planet 9 should have been able to be seen in ACT. It also should have been seen in pan-stars over here too. And then the sort of medium one could just have been at the detection threshold. Long story short, we didn't find it, but have placed kind of interesting limits on the distance that Planet 9 could be at. Because just to note, millimeter data is great at looking for it because the signal only drops as 1 over r squared, as opposed to 1 over r to the 4, because you're not looking at reflected light. So that's kind of fun. You can look at the Big Bang and you can also look for planets. Okay, so we get this, ACT is giving us this unique view of the early universe, covering half the sky, and is really complementary to Planck, and is revealing both cosmology, but also cool new stuff about the millimeter sky. And all of the things I talked about will be of interest for Simon's Observatory, which has really big UK involvement and Cambridge involvement going forward. Thank you.
Thank you, Jo. Really fascinating, great presentation. Impressive how much